All right, welcome to lesson 6. Today we're going to be looking at polynomial functions again, and this time comparing different functions together with one another, even though they might be represented differently. So you can imagine, one might be represented with a graph, and then you might be given the equation for another polynomial, and we want to be able to compare the two of them. Let's go ahead and get started. All right, so let's get started. And to begin with, we have these 4 situations, all of which are represented graphically. And for each of these, you're going to name a specific interval. And I want to say something really briefly about the word interval, because you've seen this before, and I want to make sure that you understand exactly what it means. An interval is just a set of numbers, or in this case, since we're talking about a graph, the interval is referring to a set of x values. So for these questions, let's take number 1, for example. You want to name the interval in which the function is negative. In other words, you want to name the x values for which the function is negative. And so what you can do is, once you find the spot where the function is negative, let's just do 1 together. So if we take a look at 1, we notice that the function is negative between -2 and 1. And the way that we can say this, instead of saying all x values greater than or equal to 2 and less than or equal to 1, what we can say is that it is negative on the interval between -2 and -1. Now these square brackets mean that you're including -2 and -1 in your interval. But notice that's not quite true. At -2 and -1, the value of the function is 0, and we want to know when it's negative. So what we would want to do is use what's called the curled brackets. And this means between -2 and -1, the function is negative, but not including -2 or -1. So that would be one interval. For number 1, there is one more interval, so I want you to find that one on your own. Then go ahead and complete number 2, number 3, and number 4. For each of these, you don't need to draw a very detailed sketch of the graph. Just have a basic sketch of the graph and mark any x values that you need to in order to answer the question. So go ahead and complete those, and then we'll talk about them together. All right, so let's take a look at number 2. I'm not going to write down the interval. I'm going to say them. So that way, if you got them wrong, go ahead and correct your work and make a little comment on why you made the error, and that will give you some practice with creating the intervals, and we can talk about them tomorrow. So name the interval where the function is increasing. If something is increasing, right, that means that as you're moving to the right, the value of the function will be moving upward. So notice that as we begin from the left, the function is decreasing because the value of the function is getting smaller, getting lower. But then it looks like at -2, it starts to be moving upward again. And that seems to be happening, maybe until you get to 1, and then it starts decreasing again. So the interval on which the function is increasing would be from -2 to +1. And again, you can use curly brackets here because it's really unclear whether it's actually increasing right at -2 or right at 1, and you can explain. Name the interval in which the function is positive. And so here we're looking for where the function value is greater than 0. In other words, above the x-axis. So notice between, let's see here, this is -1, 2, 3, and 4. To the left of -4, it is positive. And so we can either say when x is less than -4, or you could write an interval, and I'll let you think about what that might be, to say that everywhere to the left of -4, it is positive. And it's also positive between these 2 points here. And so you can think about what those 2 points are. And it's also going to be positive to the right of this point here. All right, the last one, name the interval in which the function is decreasing. And here again, we're looking for where, as I move to the right, the function value is going to be getting smaller. And so notice if I start from the left, it seems like the function's growing, 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 and then at some point here it begins to start decreasing again. So you might say this is, maybe starting at -1/2, and then going all the way to 2, it's decreasing, and you can explain why that is. So what we want to take away from this is a couple of things. The first is that we can tell a lot about what a function is doing by looking at the graphical representation. And so even when we're not given a graphical representation, maybe we're just given the equation, we still want to be able to create a graph so that we can quickly analyze certain situations or name intervals. And so that's going to be a key point that we're going to take with us. So let's go ahead and jot down a couple of notes now. So here's the key point. When dealing with functions that are represented in different ways, so you might get an equation, you might get a graph, you might get a table, we need to use what we know about these functions. And what do we know about polynomial functions? Well, we actually know quite a bit, right? We can tell a lot about the roots and the end behavior of a function by looking at its degree and by looking at its linear factors. And in looking at these certain characteristics, remember we talked about how we can actually graph a function or write an equation of a function. And so what we can do is if we're given an equation, we can use what we know to create a graph. If we're given a table, we can use what we know to create a graph. And sometimes that can be the most helpful representation. I'm just going to say right now, I think graphing is a key representation. So whenever I can, I always graph the function. And so if we are given a function in a representation, and it can be in different ways, we can use what we know about the end behaviors by looking at the degree and the roots by looking at the linear factors to go from one representation to another in order to draw conclusions. So just as we saw previously, if we had a graph, we could draw conclusions by looking at the graph. And if we have an equation, we can use what we know about that equation to create a graph and to draw some conclusions from that, or similarly from a table. All right, so I'm going to give you one to try, and we'll take a look at it together, but make sure you have a solution coming into class tomorrow. Let's take a look. All right, so here's the situation. A function f is given by f of x equals x plus 5 times x minus 6 times x plus 2, and the function g is graphed below, so here is g. Question A says, which function is always increasing for x values less than negative 5? Part B, name an interval where both functions are decreasing and explain how you know. And then part C, what is the average rate of change of the function f between x equals negative 5 and x equals 6? So take that key point we just talked about and use it to your advantage, right? How can you put these functions into representations that will be really helpful? And then go ahead and answer parts A, B, and C so that you're ready to discuss them tomorrow.